Okay, so today we're talking about custom iterators, and this is kind of really important for assignment 3, because in assignment 3 you are asked to define a custom iterator, and about half the marks of assignment 3 are based on doing this correctly. So we've seen iterators already, we've used them quite a lot. So iterators are classes themselves that support an abstract model of how you move over a sequence of objects. And they're kind of similar to pointers. Sometimes iterators use pointers, but sometimes iterators can just directly reference or do something with the data to go over it. And iterators are the glue between containers and generic algorithms. So containers being our STL containers or containers that we developed ourselves, e.g. the graph container that we're creating in assignment 2, assignment 3, and generic algorithms, hash include algorithm. And then you can use things like standard find if, standard copy, etc. For iterators are the glue that plug the containers and algorithms together. And so the design of algorithms don't have to care about how the various data structures work, and the designers of containers don't have to care about how the algorithms work, provided that they define an iterator that the compiler knows how to work with. And so an iterator for container might look like this. It's got a.begin, which is a pointer, hand-wavy pointer, to the first element, and an end function, which is a pointer, again hand-waving, to something that is one past the last element. In the case of an array, this is simple because it's sequential. In the case of a vector, it's typically also sequential. In the case of something like some sort of tree structure, this becomes a little bit more difficult. But you can still have an iterator over a tree. It just has to know how to move through that tree. Does it do a depth first search? Does it do a breadth first search? How does it move over the tree? And so if P, for iterator, P points to the case element, okay, so some element in there, then star P dereferences to that actual value or the actual object that's being pointed to, and plus P, okay, so pre-increment, points to the k plus 1 element. And what we want to do is create some sort of loop. So for auto, first is equal to a.begin, first is not equal to a.end, plus first. And then do something on the dereference of first. Iterators, easy. We've done them all semester in terms of how we use them. And so you can get an iterator over a vector, you can get an iterator over a list, and the for loops look exactly identical. They look completely identical because also we can use auto up here to not worry about the type of this iterator. Even though this auto type here, this iterator is actually a vector iterator and this is a list iterator, we don't care about that because the rest of this loop looks exactly identical. And so if you look at the test cases for assignment 3, the test cases with the iterators are all using auto because you need to go generate your own class that needs to behave correctly. I'm deliberately leaving this a little bit vague, so I'm just going to test your stuff with auto. Okay, so your test stuff should work exactly the same as any other standard iterator. Now, in the second week of the course, we looked at the fact that there's 5 categories of iterators. There's output, input, forward, bidirectional, and random. An output iterator, ironically, writes data into the container. An input iterator, funnily enough, can't actually write data into the container, only can read data out of the container. A forward iterator can do both. A bidirectional iterator can move backwards and forward through a container, and a random access iterator can just automatically go to any place in that sequence. And so these things are hierarchical, they increase their power. For assignment 3, I'm only requiring you to do an input iterator. It does not need to be a forward iterator, which means it does not need to update the data. This is an important point because to make this have to be able to update for data introduces a whole nother world of difficulty when we're talking about the graph. Okay, so it's only an input iterator, it's only able to dereference to constant values on the data. Okay, in fact, it should not. Your iterator in assignment 3 should not allow you to modify for data. And I would set up some type traits test to check this. I haven't written that test yet, but I'll set up some type traits test to test this as part of the marking for it. And so different algorithms, different STL algorithms require different kinds of iterators for operations. So something like find and equals, that only requires an input iterator. Something like copy only requires an output iterator. But an STL algorithm like replace requires that forward iterator, that output and input. Something like sort in particular requires a random access iterator. STL sort requires a random access iterator, which is why you can't do sort on a standard list, because a standard list does not provide random access. That's why the standard list has its own sorting function. And one more point to keep in the back of our minds is in terms of performance, it's better to do a pre-increment than a post-increment because the data of how these things actually works, pre-increment is more efficient because it doesn't require temporary variables. Okay, so this is just something to keep in the back of your mind. We talked about this a couple of weeks ago. So this is all just revision up until this point. So on Monday we talked about iterator traits. Well, I didn't talk about iterator traits, but we talked about type traits. And so type traits are a way that we can determine, there's a way in which we can determine that there's certain properties of types. And so the type traits we looked at on Monday were basically looking at things like are things const, are things numeric, are things a pointer, are things a reference, and also we looked at can we modify the types of things using the type traits library. Iterators, what defines an iterator? It's not the mere fact that the class is called iterator. What defines an iterator is certain traits, certain properties. And so the compiler is able to work out something's an iterator based off those particular type traits, those particular properties of the iterator class that you define. And there's 5 type traits that define an iterator or tell the compiler that a particular class can be used as an iterator. And they're defined in these type defs. So these type definitions define that if this thing is to be used as an iterator, this is what it needs to be able to do. And so what you're looking at is you have an iterator category tag. And so this iterator category type def says if this thing is a random access iterator, says this is an input iterator, an output iterator, etc. Okay, so the first one of these 5 things is the category of the type of iterator it is. The next ones are the value type. The value type is the type of the thing that you're iterating over. So the value type for a container of ints, the value type is int. The pointer type over the container of things that you're iterating over is int star if it was a container of ints. The reference type is int ampersand because it's the reference type. Now, there's one extra thing here, this difference type. It basically is always ptr diff underscore t. Okay, so it should basically stay like that. For difference type, it's just about always like that. And so when we write our custom iterators, we have to define these 5 type defs for our type. These 5 type defs tell the compiler that this is an iterator class. Okay, so what we're going to do is we're going to go write, I'm going to show you some code of how to write an iterator class. And we're going to spend the next 40 odd minutes stepping through how this works. Okay, so here's some code for writing a forward iterator. Contains list.hppp, list iterator.hppp, and a list user.cpp code. Okay, now list is the class template, list iterator is also a class template, and hopefully these screens don't stuff up as I try to switch back to getting my laptop to display back up here. Oops, and if I don't close the file, I just need it. Okay, so what we've got on the screen is we've got list HPPP, and list HPPP is a linked list. It's a C++ linked list. Okay, what it has, and we've seen this a few weeks ago with the stack, it's a similar idea. Okay, it's a templated list, so it means it can store generic types. Okay, it has a constructor for creating a new list. It has destructor, isEmpty, pushback functions. Okay, all our standard linked list functions. Inside it has a private inner class of node, which is a wrapper around the data that's being stored at each point, and this node has a pointer off to the next node. It's a standard implementation of a linked list. Okay? The new bits that go into this class to make it work with an iterator. By the way, this is not for iterator. This is not for iterator, this is for linked list. Okay? But to make this work with the linked list iterator, for extra things that need to go in, is this class needs to be friends with the list iterator class. Because the list iterator class might need to access its private data. As we'll see, it needs to access the private node data. That's what's a friend. What it also needs is these functions called begin and end. Now, begin and end, what they do is they, first of all, return an iterator. Now, this iterator that's returning is just this type def list iterator up here. So if you didn't have this type def up the top of here, you don't need it. All you need to do is, instead of doing that, you go and put that like that, and that one into there. And this works the same, because that type def is just an alias. Okay? And so this begin and this end function is returning, not a reference, it's returning a copy or a new list iterator. It's returning a type. So begin returns an iterator, end returns an iterator. They are two different objects in memory. Okay? And what they're doing is inside begin and end, they are going and creating, let me just put this type def back in, they are going and creating this iterator type. And we've obviously got a constructor. We'll get to the for iterator class in a second, but clearly we've got a constructor for iterator that takes in a pointer, whereabouts the pointer for begin is head, the start of the linked list, and the end in our situation is a null pointer. The reason why it's a null pointer is because at the end of our linked list, what is the end? How do we know there's the end? It's because the next thing is null. So in our linked list, one past the end is a null pointer. Makes sense, right? Okay? So we've got our begin, we've got our end, we have our container. Okay? What we now have is we have our list iterator class. Okay? So this is inside, in this example, list iterator.hppp. In your assignment, you just put this all on the one graph.hppp file. Okay? This is a separate class. It's not an inner class of the list. It's completely separate. Okay? But they're related because this is a list iterator class that goes over that list that we created. This list iterator class is very important. This is how you write a custom iterator. This is a custom iterator. So what we're looking at is, again, for this iterator class is a templated class, because we're going over a container of templated items. It has these 5 type defs defined. For difference type, which is always standard pointer diff. For iterator category, what we saw before, if we go back up a few slides, what we saw before was this one was a random access iterator tag. Okay? This one that we've done for list iterator is a forward iterator tag, which means that you can move forward through the collection. You can't move back. You can't do random. Okay, but you can move forward through the list container. And because of the forward iterator tag, you can both read and write to it. The value type for pointer type and reference type are all the same, as being type T star, and type ampersand, because of what these things are returning. Okay? Now, we then have a couple of functions available that make this behave like a normal iterator. And so we have the dereference operator. So when you dereference the template iterator class, when you dereference that object, you get back a reference type. And because of these type defs, this reference type, you go back and you go, oh, the reference type is a reference to type T. Okay? I'll give you another giant hint. For assignment 3, because this is a forward, because it's an input iterator only, and you don't want people to modify your data, you might pass back as your reference type a const reference, like that. Okay? But in this case, we're just passing back a normal reference. Okay? So we have the star operator overwritten. We have the pointer operator overwritten, the arrow operator overwritten. And that is returning just the address of the operator star. So operator star was a dereference onto that type. We then just return the address of that to make it behave like a pointer. We then have the plus plus operator defined, okay, to move on to the next thing. We have the equals and the not equals operator to define. The equals operator for the iterators is defining or checking that the two iterator objects are equal or not equal. The reason for this is you need to know when you are at the end. You need to know when your iterator, the begin and the end, is equal so that you're at the end. You also have the constructor. Okay, so the constructor for this list iterator takes in a pointer. In this case, it's taking in a pointer to a list T node object. And it can do that because it was a friend. So even though that node is an inner class within the list object, it can take in a pointer to it because it's a friend. It defaults to a null pointer. If you just go and create a list iterator over this thing, it will be a null pointer list iterator, e.g. it will be a pointer to the end. And this list iterator container also contains some private data, okay, because it needs to know what it's iterating over. In this case, it's containing a pointer again off to the thing that's currently pointing to. Okay, so that particular node internal struct of that list. And then you can go in, you can download this code, but you can go in and you can take a look at how the dereference works, which it just returns the element that's pointing to as a reference. You can return the plus plus operator. Plus plus operator is simply going through and seeing what's pointing to next and moving that pointer on, okay? And the double equals is literally seeing if these two pointer objects are equal or not equal. Waving over these last three things just a little bit quickly because in your assignment, you might have to do it quite differently. One of the straight reasons why you need to do it a little bit differently is because you might be dealing with smart pointers and not raw pointers, okay? But you might need to do some of this differently in assignment 3, but this gets you the general idea. Okay, so let's dissect this custom iterator. We kind of have already, okay? But what's the important points? The type defs are important. The reason why the type defs are important is because they are telling the compiler and telling classes that are using this code, this is an iterator. Those type defs define this as an iterator. For overload, the star and arrow operators are important because they cause us to be able to dereference to the correct values. The equality operators are important because they allow us to tell us when we're at the beginning and when we're at the end and when to stop for our loop. The constructor, of course, is important because it needs to know how to construct the list iterator type. The private data is important because, like we just seen, the private data in this instance is a pointer to a private inner class, which is a friend, but that private data is important because the list iterator is storing some data. In this case, it's a pointer, but the list iterator is storing some data, okay? The list iterator is not magic, and it does not modify, so it's probably a very important thing, except through the reference, it does not modify the internal data of the list object. When the list iterator moves on, it modifies its private data. It does not modify the list container's data. And also the plus plus operator knows how the inner class works to move on to the next item in the sequence. Okay? The plus plus operator needs to know how the inner class works to move on to the next item in the sequence. So the plus plus operator needs to know that within node there is this pointer to next that it can use to move on. Okay? That's the key points in the iterator class. The key points in the list class is simply that there's a beginning and end function that return this custom iterator type. So there's a linkage that goes on both sides of things. Okay? But what we're focusing on is this iterator class itself. Again, let's talk about assignment 3. Okay? So the custom input iterator, or a custom input iterator, is required for assignment 3. To be valid, it needs to adhere correctly to the requirements for an input iterator. And these are defined in the links below, so I've already brought them up. And you can go find them on the extra readings links page of the home page of the course, and go take a look at input iterator for cppreference.com and also for SGI. What they look like is this. This is the formal definition, or the required definition for what makes an input iterator a valid input iterator. And this is what I will check your code against for assignment 3. Okay? So, an input iterator, as we already know, is an iterator can read from a pointer to element. They only guarantee validity for a single pass. It means that you're only going forward. It's nothing about going back. Okay? And once an input iterator has been incremented, okay, so plus plus, any copies of the previous values that might have been referring to are invalidated. Okay? So if I create a copy of the iterator, and then I move on one of those copies, not the other one, that just invalidates. Okay? It may not invalidate in your code, but formally it invalidates. Okay? So I only move forward once and through it, and then there's some requirements. Okay? First of all, an input iterator satisfies, first of all, it's an iterator. That's the type defs that are required. It satisfies that things are equality comparable. Okay, that just means I can compare two input iterator types in order to do the begin not equal to end. Okay. The values for the input iterator, okay, can be of IT, just being a normal iterator, or can be const. Okay. The reference should dereference to a reference type, and the value should dereference to a value type. Okay? This means that when I dereference, so star dereference my iterator type, I get a reference back. Okay? I don't get a value, I don't get a pointer. When I dereference, I get a reference back. Okay? And then, in order for this to satisfy the requirements of an input iterator, the following must be valid and be specified correctly. Okay? So if I and j are both iterators, okay, not values, if I and j are both iterators, okay, I not equal to j must return a bool, okay, and there's a precondition on that, which is I and j are both in the domain of double equals, which simply means that I and j are both iterators over the same container. Okay, I could create two graphs. I could create an iterator over graph A and an iterator over graph B, but it doesn't make much sense to me to say that iterator for first iterator over the first graph is equal or not equal to iterator over the second graph. That doesn't make logical sense, okay? So what this is saying is a precondition is when I check that these two iterators are equal, they have to be over the same container, okay? When I dereference, so star I, when I dereference an iterator, first of all it returns a reference, and second of all, that reference can be converted to a value type, which makes sense. If I get a reference to a double, I should be able to assign that reference to a new double. That's not a reference, just assign that reference to a new double, and that should all work. Okay? And if, again, if you've got I, which is equal to j in the same domain, then dereference of I should be equal to the dereference of j. Okay? First of all, it's a precondition that the iterator is dereferenceable. Okay? So you need to make sure it can dereference. I pointing to m is equivalent to the dereference of I dot m. Again, precondition is I is dereferenceable. I've personally found that particular requirement of getting the arrow to be quite difficult to use. Okay? And so I may or may not check for it. That's probably going to be one of the more tougher ones to do is with a smart point is get the arrow operator working. Plus plus I, first of all, it returns a reference to the iterator itself because that's how the pre-increment should work. And it requires that, first of all, I to be dereferenceable as all these other preconditions are required. It has a post-condition that either the return type is dereferenceable or it's one past the end, which would in our case be this null pointer. And if it's one past the end, then it's not going to work. Okay? And there's also a post-condition that any copies of a previous value of I are no longer required to be dereferenceable or to be in the domain of double equals, which simply means that if I go and move an iterator on and I have a copy of the iterator, that iterator I had a copy of may or may not be in a valid state, basically. Okay? So this is just saying, as I use your iterator as part of this post-condition, I'm not going to go and do dumb things with it. The expression I++ has got to be equivalent to plus plus I. Again, I won't necessarily check that. This is the fun one. Dereference I++ should be equivalent to moving it on and then dereferencing it. That's basically what it's saying. Okay. Again, this last one I might not completely check, but these are the properties of how an input iterator works. A really key take-home message is that these things should be const for the case of the input iterator. Okay? And I'm going to check that these things are const by literally doing a dereference. First of all, checking that you have a reference coming back, and then secondly, checking that the reference that has come back is const using type trace. Okay? Now, the second article we've got over here is again very similar. Okay, it's just a different article, but it's telling you exactly the same stuff to do with how these things should work and what the return types should be and what their behaviour is. Okay. And finally, one of the other articles you can read again on sgi.com goes into a whole lot of details about all the different types of concepts and iterator types and functions that can work on them. Okay? But you don't need to focus too much on this. What you need to focus on is just getting the custom input iterator to work. Now, what other notes do I have? Okay, so the input iterator does not allow for data to be modified, hence use const. Okay, so let's talk about using smart pointers with iterators. So, again, talking about assignment 3, one of the requirements for assignment 3 is your iterator needs to come over a particular ordering of the graph. And that ordering is based on the number of edges connected in to each node. And if the number of edges into each node is equal, then it's a less than comparison on the node values. Okay? Now, that requirement is both very easy and very difficult. The reason why it's very difficult is because some people already on the message boards are asking, going, oh, I've got to store this thing in order, and say when someone inserts a new node or deletes a node or inserts an edge or something, I need to reorder my whole structure at that point. I personally think it's a really silly way to go down. The reason why I think it's a really, really silly way to go is, for example, if I could actually set up a test case that inserts a whole ton of stuff, deletes a whole ton of stuff, just keeps on hitting your reading and writing functions of your graph. And I never call print or an iterator that requires the stuff to be sorted. And so you're doing all this heavy sorting as you go, and it's kind of redundant. Okay? So you should only sort when you are required to sort. Okay? When are you required to sort? The couple of times in the assignment you're required to sort is when you get an iterator and when you get print. I can't remember off the top of my head if there's any other ones, but when you get those calls is when you should sort. Now, in terms of when you should sort at that point, again, this is a design decision for you guys to make. Okay? But as part of that design decision to make is when you get called to go and create a custom iterator, are you then going to go and sort all your underlying actual internal structure of your graph? Or, alternatively, are you going to do something really interesting, and this is again a giant hint, are you going to do something interesting whereabouts using smart pointers, so shared pointers, weak pointers, etc. Could you, inside your custom iterator, rather than just having a constructor that takes in, just like say the head in this example up here, could you pass in almost, dare I say it, a whole container of pointers? And that container of pointers is the sorted order in which you work through your container. And if you can do that, does that not make the custom iterator really easy to do? Because when you get for plus plus increment, all that you need to do is pop the head off that container. And you know what you're at for end when that container size is 0. And when you need to call for dereference, so the star dereference, maybe all you need to do is return a constant reference to the head pointer inside that container. Now, the trick that you've got to do still to do this is you still need to figure out the sort. You still need to figure out your custom iterator container. Okay, there's still a lot to do, but can you do something very interesting with smart pointers that basically over your graph, you do not need to change the data structure of your graph. You can do whatever data structure you like with your underlying graph. It's only when you get called to create this custom iterator. Could you do something interesting at that point? Okay, I'm just going to leave that for you guys to think about. It is challenging, okay? I'm going to leave that for you guys to think about, but your custom iterator, take-home messages. This is probably quite a strange lecture because I'm not exactly going through the stuff in secrets. Take-home messages. Your custom iterator needs to have these things defined, okay? But there's no rule that says that your custom iterator has to just store a singular pointer to a singular object. There's no rule about that. What the rules are that your custom iterator needs these type defs defined, needs these particular properties and these particular behavior defined. Okay, so they need to know how to dereference, they need to know how to move on. In case of an input iterator, it needs to be const, so you can't modify the stuff. But for the most part, it doesn't need to do much more. Okay, and I'm trying to make this both easy but challenging at the same time. What I mean by easy and challenging is it's easy because you should be able to grab the code that I've put up here and go and modify it. The real challenging thing is there's actually not a huge amount of, if I go and Google search how to create a custom iterator out there, or for instructions for creating custom iterators that are online, there's lots and lots and lots of different examples. Follow these examples that you've been given. There's actually one more link I'll quickly show you, which is using another web page, again available off the links page, defining custom iterators. This one talks about how you might do begin and end, how you might store, how you might do the not equals and the dereference and the plus plus and things like that. Okay? Is there any questions at this point? Yep.
How is a graph ordered?
How is a graph ordered? That's for you to figure out.
But in there, oh, do they? Oh, it's just.
Sorry. So what's your question? How is a graph in general ordered, or how is the graph in the assignment ordered?
I mean, like, what is the order of the graph?
What is the order of the graph? So if we go take a look at the assignment, okay? The assignment basically says, okay, I'm going to start with a mathematical definition of a graph, okay? Because some people seem to be really struggling on this, okay? Step one, this is a directed graph. This is a directed graph. I can't be any more clear than this, okay? Because people seem to be confused about that. This is a directed graph. That means that I can have two nodes, A and B. I can have an edge from A to B. It does not mean I have an edge from B to A. Okay, this is a directed graph. Mathematically defined, my graph has a set of nodes. What that means is the mathematical definition of a set. A mathematical definition of a set means you don't have duplicates. Okay? That means that if I have, say, a node of chars or a node of strings or something, if I have a node that contains the value A, I cannot insert another node containing the value A because this is a set. So the graph is a set of nodes. That means there's no duplicate data values. What it also means, though, is say if I had a graph that was a set of pointers to strings, and I had a pointer to a string containing value A, I had a second pointer pointing to a second value A that was in a different location in memory, then I could have that duplicate A value because it's not a duplicate in the sense of A, it's a duplicate. Well, it's actually not a duplicate because the graph is over a set of pointers. Okay? So you have a set of values, which is your type T. Okay? Or in the case of the assignment specification, it's over type N. Okay? But you have the graph over that particular data type. So a set of nodes. Your set of edges, again, use the word set. Your set of edges, you can think of like this. Every node, not the graph, every node has a set of edges. The definition of an edge is an edge has, it can be two different definitions of the edge, but it has the same meaning. An edge can be defined as a tuple of origin, destination, weight. Okay, that is one way you can define it. Tuple of origin, destination, weight. If you go for that definition, it means that you can have inside your graph a set of all edges. Alternatively, you can go for the definition of an edge being just simply a destination and a weight. So it's a pair, destination and weight. And that is whereabouts you have on each node a set of those pairs. Okay? Up to you. You can go for either of those definitions. You can go for some other sort of definition, but for take-home message in terms of the definitions of the structures is you have a graph, it is directed, and it's got a set of nodes, which means there's no duplicates. It's got, for each node, a set of edges, whereabouts the edges have a weight value and a destination. And there cannot be duplicate edges, which means that if I have an edge from A to B with the weight value of 1, I cannot insert a second edge value from A to B with a weight value of 1, but I can insert a second edge from A to B with a weight value 2, because that weight value is different, and therefore those two edges are different, and they still satisfy that requirement. So that's what this mathematical definition up the front is telling you. How you do that in your code, if you use actual standard tuples, standard pairs, if you use standard vectors, standard maps, standard I don't care, whatever you use, that underlying data structure I don't care about. Although you should be using some sort of STL container rather than strictly creating some mess of pointers all over the place. Okay? The place in which the pointers are required in the assignment is in exactly the same way as you see with this list container here. It's not required, but it's often a good idea to have some sort of wrapper around the types that you are storing. You will have seen this in this week's tutorial whereabouts we had wrappers around, I think it was books, oh, this was a library, and we had these containers, and we had this wrapper around for container types. The reason why you have those wrappers around for container types, for mere benefit of being able to create just pointers off to those things. And when you then delete that container, it should delete cleanly the item that's inside it. Okay? Again, it's part of the challenge of the assignment is doing that efficiently. Okay? Doing that efficiently is a big challenge, and also doing it correctly is a big challenge. Okay? So on the surface, some people look at the assignment and go, it's pretty easy. Creating a graph is the easy bit. Okay? Creating the graph is the easy bit. The challenging bit is doing this efficiently and correctly. And what I mean by that is not leaking memory. Now, smart pointers will help you out with not leaking memory, but as you hopefully have seen in the tutorial this week, you can still accidentally leak memory if you have still in somewhere floating around a shared pointer that's been reference counted. Okay? And so again, the way in which we might test this, and we're still working on building the tests and stuff like this, but the way in which we might test this is we might have a test that says you have, I don't know, 100 megs of RAM. Let's go and create arbitrarily 10 million points in our thing. I'd literally maybe create a container of graph events, and I'd literally go and create 10 million nodes in that thing. And then I'd go and delete for 10 million nodes, and then I'd go and create for 10 million nodes, and then I'd go and delete for 10 million nodes. I might do it 10 times, or 100 times, or a million times. Okay? Now, if you are correctly increasing, decreasing your memory, that memory requirement of that 100 megs you shouldn't exceed. If you have got a memory leak somewhere, you will exceed it, because even though you might have lost where those pointers were going to, you'll run out of memory. In terms of performance, what you might do is you might do exactly the same thing, but limit your performance time to, say, try to do this in 10 seconds. And again, depending on your implementation, depending on your use of weak and smart pointers, okay, depending on your underlying data structures, so are you using standard vectors, are you using standard maps, are you using whatever, okay, that 10 seconds to do that insert, delete, however many times is required, you may or may not pass, because, again, using these pointers and effectively being able to insert and delete is a real challenging problem. Okay? And so the way in which I test this is I have a reference solution that I've put together myself. As someone nicely pointed out this morning, I actually sometimes have bugs in my reference solution, and I hopefully realise all those and fix those before your tests run across them. But this is a challenging assignment. It's a challenging assignment from the perspective of thinking about these performance issues. And in terms of those sort of test cases, they're only for very, very advanced sort of, dare I say, HD sort of test cases, but they are stuff that I'll be looking for in terms of performance and marking and things like that. Okay, so the question that we had like 5 minutes ago was on the sorting. So I'm gonna come back to that question. So you've got all this requirement, okay? You've got all this requirement, and so you come down and you get to print nodes, okay? And so the requirement for print nodes is print for data stored in each node of a graph. For data stored is printed on its own line. For order of a print is from the node with the greatest number of edges to the node with the least. Two nodes are equal, edge counts, then print sorted by the lesson operator comparison of the data on both nodes. See test 1 and test 2 for an example of this. Now, just keep that in the back of your mind for a minute, and let's go take a look at the requirement for the custom iterator. Custom iterator returns an input iterator over the graph. The iterator should dereference to the data on each node. The order of iteration is from the node with the greatest number of edges to the node of the least. If the two nodes have equal edge counts, then the print is sorted by the lesson comparison of the data on both nodes. You must define your own iterator class for this requirement. Now, that print higher up and that begin, the sort is the same. So that print higher up, hint, hint, should be calling the stop begin, okay? Because otherwise you're duplicating your node, duplicating your code, maybe also duplicating your node. So this is whereabouts this is important, this custom iterator here. Okay? hint, back to what I was saying 10 minutes ago now, that begin function, hint, maybe should be doing something with the pointers, creating some sort of container, some sort of something over the pointers, passing that into the custom iterator. The custom iterator then goes and does the rest. Hint, hand wavy, go do that please. Okay. Okay, I've got about 3 minutes to go. Is there any questions at this point? No? Okay, so as you can probably see up the top, we have about 7 or 8 slides left in this presentation. I am skipping them because they're not required for assessment, but what you should take a look at it in your own time, okay, is how you can combine the type traits and custom iterators. So on Monday, we looked at the issue of, say, if we can iterate over a container and return from that container some sort of value that was in that container. And so we had, for example, about how do we do this with a custom return type and things like that. There's some examples of how you can do it. Okay, by the way, your code here should work on that code. And how it instantiates it. If you wanted to do a bidirectional iterator, defining the ---- symbol, which in the case of the list that we saw earlier, has simply a forward linked list. You just need to make it a doubly linked list, and ---- will work. Making reverse iterators work. Okay, actually, this one, some people failed some tests, or one test case on assignment 2, because I gave your constructor a reverse iterator and people couldn't handle that. I don't know why. They basically, it should have behaved like a standard iterator, and they'd done some weird code that caused it not to work. But reverse iterator just goes through your container backwards. Again, not required for assignment 2, but you should have these ideas. And again, the reverse iterator is a separate iterator type itself. C++11 style const iterators, so C begin, C end, const reverse begin, const reverse end. Not required for assignment 2, but you should have those ideas. Okay, so in summary, iterators are classes, they're types. You can define your own iterators as class templates, as we've seen. You can also define your iterators as templates or ordinary classes nested inside other classes. Please don't do that. Do it as a separate thing for assignment 3. And develop in stages. So for instructions here, go develop a forward iterator first, and then go back, and then do reverse, and then do const, etc. Don't worry about that for assignment 3. Assignment 3 is simple, hand wavy. It's simple. You're only doing an input iterator. We're done. Yep.
Just a quick question. So if we got an iterator,
Yep.
and then we add a node,
Yep.
what would happen?
So I would consider that iterator to have been invalidated because you've gone and modified the